All right, so now recording code. Number one, so the problem gives you a function for revenue, a function for cost. First, you want to take the derivative of the revenue function. That's just power rule. So that's pretty straightforward. So derivative is going to be 10 for that term, and for this one, you'll have 0.0002x. And we should maybe put units for this. So this will be dollars per toy. Okay. Now, as for interpreting the meaning, I kind of had to guess what is actually being sought after here. So in words, R prime is the rate of change of revenue. So I would write that. Rate of change of revenue is this quantity. I'm trying to figure out if there's like a better way to phrase this, but I think it's pretty much just rate of change of revenue is this if you selling X toys. Yeah, I don't know how else you would, what else you could do to describe what this function is doing. For B, it's very similar, but here you actually just get a constant. You get 2, and this will also be in terms of dollars per toy. And same thing, when you interpret this, the rate of change, it's a bit easier to write what this is since it's just a constant. So rate of change of cost will be $2 per day. Or toy, sorry, toy. And there's actually one other way you can state this in words, which is you think about this as like the kind of the incremental change. Like what happens if you increase the number of toys by 1? So if you increase the number of toys by 1 for this, since this is a constant, it makes phrasing it like this a little bit easier. Then what happens is that the cost will increase by $2. All right, so that's just yet another way you can interpret what this is saying. C, well, it's doing revenue minus cost. So what you should know about quantities like this is that we normally assign this a name. We call this the profit. So this is the profit of the situation, and we're asked to take the derivative of it. Okay, so I guess what I would do is I would write this, and then I would note that this derivative operation splits over, sorry, splits over the subtraction. So we can just really use parts A and B to answer this. So this will be R prime of X minus C prime of X. And then we can just do this minus this. So you'll have 8 minus 0.0002x. Again, this has units, so I'll just say dollars per toy. And interpreting meaning, well, just call it rate of change of profit. Right. Okay. Everyone good so far? Any questions? There's a lot less people today. Oh well. So for D, when is the derivative that you found positive and when is it negative? So P prime of X is positive. What does that mean? Well, it'll mean that 8 minus 0.0002x will be well, greater than 0. I actually I would rather move the other term to the other side and just go to this. Yeah. And then divide by this number. That'll give you x is less than 40,000. And this is toys. Okay. And then for the other inequality, it's just you swap the inequalities. 2x, and that implies x is greater than 40,000 toys. Okay. So does it make sense how I did that? It's just a little bit of algebra. So, all right. So no one's speaking up. Okay. Then E requires that you take the sort of interpret it, right? So you want to maximize the profit. Well, what this is saying is that it's going to increase, the change in profit is going to increase so long as x is less than 40,000. Then after x is 40,000, the profit starts to decrease. So we kind of expect that the sweet spot will be 40,000. So to maximize profit, make 40,000 toys. And then to figure out what is the total profit, well, you want to plug that into a profit function, which we sort of have. We have it as revenue minus cost. We didn't actually write an explicit profit function, but we can just plug it into revenue, plug it into cost, subtract the two. So when you do that, you'll get the values 240,000 minus 130,000, which will give you 110. That should be straighter than that. 110,000. And then, right, so finally it asks you to explain your reasoning. So that's pretty much the verbal explanation of how do we know that this 40,000 is the place where it maximizes. So the way you could say that is after x equals 40,000, the rate of change of the profit is negative, right? And so profit decreases. Beyond that point. Okay. So hopefully you find that convincing. Does it make sense? Yeah. No one wants to say anything. Okay. Right. So the number 2, this is just real world interpretation. So you're given a cup of hot tea, and it's asking you f prime of 3, whether that is positive or negative. So is the temperature increasing or decreasing 3 minutes after you've been given the cup? So you should definitely say that this is negative. Right? Since the temperature will decrease, I guess I did because temperature. Right, and that's simply because the beverage is hotter than the ambient temperature around it. If you were given a cold beverage, like I don't know, iced water or something, then you would expect that the change in temperature will be increasing. Right, so that should make sense. For 3, this is going to just use like every word here. You just have to translate this. So translate this statement. Okay, so W is amount of water. So this is rate of change of water. And then you have to say like, okay, 18 means 2018, and just phrase this all in words. So the way I wrote this is in 2018, the water in, and then I had to specify exactly where since it's given to me. Tuttle Creek Lake is decreasing at a rate of, and then 0.01 cubic kilometers per year, right? So the decreasing is because it's negative. The rate is because this is actually W prime, not W. Right. But apart from that, I think it's relatively straightforward. So questions? Right. So 4, I have to say one thing about 4, which is on a previous homework assignment, I think the one that you just got back, a lot of people actually, when they got a problem like this, they weren't reading the problem carefully. They only found the slope of the tangent line. They didn't find the full tangent line. So you're asked to actually find this full equation of a tangent line. That means you need to put it into point slope form afterwards, not just take the derivative, right? So, and the other thing is that we're being introduced to this cosine function that we need to take the derivative of, which is kind of new for us. Because it's part of like what we were lectured on this week. So I guess I'll start off by talking about, let me scroll off a little bit. Let's talk about the trig derivatives. So, which I also did in the previous class. So derivative of sine, as you should remember, is cosine. Derivative of cosine is negative sine. Derivative of tangent is secant squared. And you can remember these, but I don't think you're asked to. Derivative of cotangent is negative cosecant squared. Secant and cosecant. So secant has the derivative of secant tangent, and I have to be a bit more careful here. So I need to actually say this is secant x tangent x, because it's a product of two functions. And cosecant is going to be negative cosecant x cotangent x. And the reason to sort of lay out these trig functions in this way is because it's kind of the standard way that you would lay trig functions out. There's more patterns when you lay them out in this way. And in particular for derivatives, you see that things kind of split up into these families. Sine and cosine kind of behave similarly. Tangent and cotangent behave similarly. The function gets squared. And then secant and cosecant, they've got like a version of themselves, and then they have a version of the tangent function. And then you can also notice that the only functions that have negative are the co-functions. So cosine, cotangent, and cosecant, they all have a negative show up when you take their derivative. So this is one way to just remember the entire set of trig derivatives. And you'll see that there's actually going to be similar split up that happens with the arc trig functions, the inverse trig functions. That'll be a bit later in the course. One other thing that I want to mention is, so you learned and you saw that like when you take derivative of the sine function and the cosine function, if you take them like sufficiently enough times, it'll start to loop back on itself. Well, a nicer way to actually visually see this is actually just to make them show up in a loop. So derivative of sine is cosine, derivative of cosine is negative sine, and derivative of negative sine is negative cosine, and derivative of negative cosine actually brings us back. So just from this picture, you can see like, oh, they're periodic with like period 4. Like you take 4 derivatives, you get back where you started. And it's just easier to see both sine and cosine share this because they're actually part of the same loop, right? The one thing also to kind of notice from this is that this is one directional. Like you have to be going in this direction. And the reason why this is important is actually because later on, halfway through the course, you're going to start to learn about the integral, which is basically it's the reverse operation to the derivative. And so then you're going to have to kind of know how to do this in reverse. So this is where people will get kind of confused and they'll forget like which way is sine and cosine facing. So kind of like what I can recommend is try to remember this order for derivatives 100%. That way, when you start being asked what is integral of cosine, what is integral of sine, you won't get those negatives confused. Like so long as you have one order imprinted really deeply, like you shouldn't confuse the other order. Just thinking forward on that, but yeah. Okay, now let's go back to this problem. We have this and we want to find the tangent line. Okay, so, and we want to find the tangent line at this. So really, first thing we would do is take the derivative, but then we're gonna have to evaluate it. So first take the derivative, that's gonna be -5 sine, sine of x, and then we want to evaluate it at pi/4. Okay, so pi/4, hopefully you can just think through unit circle and remember sine of pi/4. Pi/4 is a 45-degree angle. Sine is going to be √2/2. So you get √2/2. And so this is your m for your tangent line, but you need to point as well. So the point is going to happen at this x value, but I need to know the y value. So I need to know y at pi/4. Well, I plug right in. Cosine actually is going to be just like sine for this angle. It's also going to be √2/2. And so we get the coordinate. I guess I can just rewrite it. The coordinate is this x coordinate and this y coordinate. And so when we write this in point slope form, we'll have y minus the y naught equals m x minus x naught, like so. Yep. And so this is the answer you're looking for, that the problem is looking for. Okay. Now number 5. So the first thing that jumps out should be that this is going to involve product rule because this is a product of two functions. All right. So we take the derivative of that. Derivative of x is just going to be 1, so you're just going to copy down the other guy, and then plus, and then you have x times derivative of sine, which is going to be cosine. So we've got that. Now the second derivative is going to require that we take the derivative of the first derivative. So we take the derivative of the answer we just got. So derivative of sine is going to be cosine. And then notice we have x times cosine x. So this term is going to require product rule. Okay, so if I take the derivative of the x, I'm just going to be left with cosine x. If I take the derivative of the cosine, I'll be left with a minus sine x. I'll just put parentheses, minus sine x, like so. Okay, well, it'd be a little bit nicer if I combine these two cosines together since I'm going to have to take the derivative for part C. So I'm going to rewrite this and clean it up a little bit. So 2 cosine x minus x times sine x. Okay, maybe I may as well box it. And now we're asked to take the third derivative. So we take the derivative of our previous answer. Okay, so derivative of 2 cosine x, that'll be -2 sine x. And then we've got this minus x sine x. So the minus is going to distribute over. I have to immediately remark that because this is going to involve a product rule. So it's going to have two terms when you take its derivative, but the minus needs to distribute over both of them. So I put a minus parenthesis. And then derivative of x is just 1. So we just copy down the other function and then plus. Now we have x times derivative of sine, which is cosine. So x cosine x. Okay. And then lastly, we can clean this up just a little bit just to make our answer look a little bit nicer. So we'll have a -3 sine x minus x cosine x. Okay. Any questions? I think I can box this as well. Yeah. No questions? Okay. Well, so number 6, these derivatives are a little bit messy, but we can still work through them. And immediately 6a makes me want to, I guess, repeat or check with you guys whether you remember what quotient rule says, because you have to remember the order of quotient rule. Okay. So hopefully you can just recite it, that it's going to be gf prime minus fg prime. You have to remember that this, like, you have to remember not to switch these two around, and then it's over g squared. Okay. And so when we do it for this problem, we'll have denominator stays times the derivative of the numerator. And so this is where we have a power rule that is a little bit bothersome, but 45 over 7 w to the negative 2 over 7 plus 5. And that is the first half of quotient rule. So we put a minus, and then we copy down the numerator times derivative of the denominator. And I'm going to have to wrap the product over here. So derivative of sine is cosine. And then derivative of that is 126. W to the 5th. And this is all over denominator squared. Okay. For B, well, it's a quotient rule yet again, but in the numerator, this time we have a product rule. So we have a product rule inside of a quotient rule. It's a bit less messy, actually. Maybe it's because the function is a little bit simpler. So first we copy down the denominator times now derivative of the numerator. So we need to do product rule for this numerator. And yeah, so what's nice is actually things combine when you take the derivative. So derivative of sine is going to be cosine. So I may as well write that as cosine squared theta. And then normally we would have a plus because of product rule. But the thing we're taking the derivative of is going to be cosine, which will give me a negative. So we'll actually have a negative in front, and it'll be negative sine squared theta. And now second half of quotient rule, put a minus, and it'll be numerator times derivative of denominator. Derivative of denominator, it's going to just be this. So that's just a pattern that you can remember, right? If you take the derivative of the square root of x, it's 1 over 2 square root x. It's if you don't know that, then what you would do is you think of the square root as a 1/2 power, and you do a power rule. And then if you rewrite it, you'll get this format. So, okay, and then this is all over denominator squared. So that squaring is going to get rid of the square root, which means I'll just have a theta on the bottom. And so that's part B. Any questions so far? No? Okay. Part C. So the thing about this is this notation is actually a little bit, it tricks you a little bit. So because when you see this cosine to the 7, a lot of the time, people will make the mistake and they'll take two derivatives in one go. They'll take so what I will do is I'll write this as what it actually is. It's cosine of x and then raised to the 7th. And this guy is also something that I need to rewrite, tangent of x, which is then squared. Right, writing it this way lets us see that we actually have a function inside of another function. We have the cosine function inside of the raising to the 7th function, tangent raised inside of a squaring function. So the way that we take the derivative for these is we actually need to use chain rule. And so chain rule is something that you're introduced to for this week. So I guess I'll do a quick refresher on that. So chain rule applies when you have a function inside of another function and you're trying to take its derivative. So, and the way that you think about this is you always take the derivative of the outermost function, and then you just stick the contents back in, and then you take the derivative of the inner function afterwards. So you multiply that by the derivative of whatever the inside guy will be. And this is important for when you have even more nesting of functions. So let's put now a function h inside a function g, which is inside a function f. And so then the way that chain rule works for this is we take the derivative of the outermost function, just leave the contents inside the same. I think that's 3 parentheses, yeah. And then we have a product. And now we have to take the derivative of the inner function. So the inner function is this g of h of x, right, which you can see either here or you can see it in here. I actually tend to see it inside of that. And then what happens is you take its derivative. Well, that's just going to be yet another chain rule. So you do a g prime, and then you leave the inner function as is, which is going to give you h of x, and then you times by the derivative of the inner function, which is like that. And then finally it stops because there's no more inner functions. And so one thing I like to term is, which I think is a non-standard term, but I like to say that the tailing part is like the chain rule piece. It's the part that like shows up because of chain rule that keeps extending on and on until finally it terminates. Okay, well, we'll see that used in part C and then in part F as well. Part F actually has 4 functions inside each other. Okay. Well, for C though, this is just 2 functions, right? We've got cosine, we've got the 7th. So when we take the derivative of this, it's going to be 28. And then so first thing I'm doing is the outermost function, which is this raising to the 7th. So I'm doing power rule first. Okay, the power rule is the first derivative that I'm applying. So we're going to have a cosine to the 6th, which I can just write in this kind of shorthand form. Okay, but then we have to do chain rule. We have to apply chain rule, which says derivative of the cosine, which is negative sine. Okay, and now I'm done. Now I'm done with the first term. The second term, that's pretty straightforward. You just have to remember what is derivative of secant. So that's secant tangent. And then the last term, well, we have the power again. So power rule followed by chain rule. So this is going to be 156. Yeah, 156 tangent. So that is just from the derivative of the square, the power function. And then I have to tack on the chain rule piece, which says derivative of tangent is secant squared. Okay, so we get all that for this answer. Okay, D is not so bad. D is just product rule. Okay, because this is a product of 2 functions. So first we take the derivative of the square root function, let's say. And so we get 2 square root t times secant t, and then plus, and then it'll be square root of t times, now derivative of secant, again, is secant tangent. So we just write that down, secant t tangent t. And just notice also, like, I'm being careful to use the same variable that I'm given. It makes a lot more sense to do that, right? Okay. So that's D. All right. E. So I explained to you guys the generalized product rule. Hopefully you were there for that. But if not, then the idea is that, so if you have multiple functions that are being multiplied together, it's going to be some kind of a product rule. And the shape of this result is going to be 3 terms in this case, because there are 3 functions being multiplied. So you have 3 terms, and each term is going to have one of the functions being the derivative and the other two are just going to be copied down directly. So we'll start by taking the derivative of the sine. That'll be cosine, and helpfully here that actually will double up with the cosine. So we'll end up with a cosine squared x tangent x, and that'll be one term. The second term, we will take the derivative of the cosine, and then we multiply by the other two guys. So the derivative of the cosine is actually going to be negative sine. So actually, I need to erase this and put a minus, and then sine squared x tangent x. And then the last term is going to be derivative of tangent times the other two functions. So tangent's derivative is going to be secant squared. I could just write the other two guys, cosine, and then secant squared x. Yep. Maybe if you want, you can emphasize by putting multiplications there. Okay. But yeah, so then that's basically it. Some of you might notice that you can actually simplify this a little bit. There are some trig things that we could do to simplify, like actually this term simplifies and this term simplifies, but let's not bother with that because writing it like this makes it clearer to the grader actually what you did. What you did is you use a generalized product rule. Okay. Simplifying will only maybe introduce possibility of error. So let's just leave it as such and continue to f. So f, we have four functions, right? So you got sine, cosine, and then this 7 theta. 7 multiplication by 7 is still kind of a function. So when you take its derivative, you're going to get something that comes out. Okay, so the way chain rule works, right, is you take the derivative of the outermost function, and then you are just unpeeling the function as you move on. So here we got cosine, and then we just copy down all the inner contents. I think I need 3 parentheses. And then we take the derivative of the inner function, which is the sine of cosine of 7 theta. So that function, sine cosine 7 theta, the outermost function is the sine. So I need to take its derivative, which is going to give me cosine. Cosine, and then we copy down the function inside of that, which is going to be cosine of 7 theta. Cosine 7 theta. And now chain rule says we take the derivative of the inner function here. That is cosine of 7 theta. We take the derivative of cosine 7 theta. That's going to give me a negative sine. And then copy down the inner function, 7 theta. And then lastly, we do chain rule yet again. So then derivative of the inner function, which inner function is 7 theta. Take its derivative, we get 7. And one way we can kind of illustrate what's happening is I'm going to note like what are these inner functions that I'm sort of expanding out. So over here, for this first term, the inner function is the sine of cosine of 7 theta. And then everything that tails afterwards is actually the derivative of that. It's the chain rule piece, is all of that. And the way we would get that is, well, we would have the outer guy, take the derivative of the outer guy, which is the sine, and you would copy down cosine 7 theta. And then notice this is the inner function for the rest of the chain rule. So it keeps like sort of unwinding itself. This guy, this cosine 7 theta, we would take its derivative, we get negative sine because that's the derivative of cosine, and then we would leave the 7 theta because that's the inner function for this. And then lastly, we have that function, which gives us the 7. So this is kind of the way I'm visually seeing that this is the derivative. Like this is how I'm visualizing the chain rule process, is I'm unwrapping the functions. Okay. Any questions? No? Okay. All right, then there's next problem. So C prime of 1. We want to calculate C prime of 1, given that C is this f of g of x. So this is just going to be a chain rule, and then we would evaluate at 1. So what I would do to save time is I would actually immediately write down C prime of 1 instead of writing down C prime of x and then plugging in 1. That's, I don't know if everyone is comfortable with doing it like that. You could like what I'm basically doing here is I'm going to be doing two steps in one go. So, all right. So, right, this equality is gotten by first you take c prime of x, take the derivative of this function, and then you evaluate at x equals 1. And so then you'll get this. And then all you have to do is plug things in, reading off the table. So we're gonna still have this f prime. We need to calculate g of 1, which is 4 according to the table. And then we find g prime of 1, which according to the table is 2. Okay, so we get that. And then f prime of 4 is what I need. So I get 10 times 2, which is going to be 20. So that's it for that. Right. 8. Well, hopefully 8, you actually tried to do it on your own. This kind of thing is something that maybe requires a bit of practice to get used to thinking about. But it's very similar to how in the slides, how Spencer showed the derivative of tangent. So cotangent behaves just like tangent. All we need to do for this thing is just rewrite cotangent in terms of what it actually is. So you should know cotangent is not equals. Cotangent you can rewrite as cosine over sine. And so now we have the quotient of two functions, and that's where the quotient rule comes into play. So we then just take this derivative according to quotient rule. So that's going to give me sine times the derivative of cosine. So I already know that's going to be negative sine squared minus cosine times derivative of sine. So derivative of sine is cosine. We're going to get cosine squared, and then all over denominator squared. Okay, and then the only way to actually connect this with cosine squared is you have to know this identity from trigonometry. G-O-R-E-N, Pythagorean identity, which is that sine squared plus cosine squared is equal to 1. Okay, the way that this fits in is that this is actually the negative of sine squared plus cosine squared. You can factor a negative 1 out of the numerator, and then you're going to have sine squared plus cosine squared. So that reduces, the numerator reduces to negative 1 over sine squared. And then hopefully you remember that sine and cosecant are reciprocals. So that's why we can just write this as negative cosecant squared theta. So that's how this whole, I guess you could call this a derivation. This is how you derive this, this rule. It's from all of this. Okay, so probably there aren't any questions for that. So number 9 is our last problem. Early on time, actually. Right, so this one is maybe the more involved problem. There's a lot of words and the units are a little bit strange, maybe thousands of people, parts per million. But the one thing that is useful to check here is that you can just compose this carbon monoxide function with this population function. You don't have to do any conversions to it. And that is true because this is the carbon monoxide function wants the input to be in thousands of people. And the population function outputs in terms of thousands of people. So we can just plug one into the other without worry. That's good. The next thing is to understand what is the problem actually asking us to find. So the rate that the carbon monoxide level will be changing with respect to time 5 years from now. Okay, so it wants us to find this carbon monoxide function, but with a derivative with respect to time, which is slightly different because you notice that the input variable here is actually population. So you really do need to think of this as carbon monoxide, and then you nest in the population function. So now this composite function is a function with respect to time that you can actually think of taking the time derivative for. And then the last thing is you want to find it 5 years from now. So all of this will give you a function with respect to time, and then you're going to want to evaluate this at time equals 5 years. Okay. What I'm going to do is I'm going to avoid actually creating this nested function though. And that's because it kind of is already bad enough to try to take the derivative of this carbon monoxide function. To try to create the combined function that takes derivative looks very messy. So instead, what we're going to do is we're going to actually use the same technique from number 7, where I took the derivative of this thing that has chain rule involved in it. I'm going to take the derivative and I'm going to plug in the 5. Same kind of pattern. Okay, so we have CO, this function. We will take its derivative, and then we will plug in P of 5, and then multiply by P prime evaluated at 5. So hopefully you're convinced that this is going to be exactly the same thing as this. Okay. And I'll remark one thing. This prime here actually is not a derivative with respect to time, but it's with respect to P. This is respect to the population. So this is the derivative for this carbon monoxide function. So now we have basically the template for what we need to actually evaluate. I'm just going to go ahead and evaluate now. Thankfully, I have all these calculations done already. Otherwise, some of these do require a calculator. So first thing I would like to do is calculate P of 5. So you would plug 5 into here, and you would get 101. That one is you may or may not be able to do that by mentally. Then another thing we're gonna need is we will have to then plug this 101 into the carbon monoxide, well, the derivative of the carbon monoxide function. So first I need to actually take the derivative. I'm gonna remark this. This is equal to dp of CO of P. Okay, just to make it clear, like that this derivative is actually a derivative with respect to P. Okay, well, now we're taking a derivative of a function with the square root. We kind of know how that works, right? So 2 square root, and then I want to say 0.5p plus 15. And then notice also that we have a chain rule. This has chain rule because the inner function is this 0.5p plus 15. And it will have a derivative that is not just like 1. It actually has a derivative that is 0.5. Okay. So this is the full CO prime function. And we can then plug in, okay? So we can then plug in CO prime of 101, because that is what this is telling us to do. And that will give us the value 0.031. This you definitely want to use a calculator for. I don't remember if it's actually, I think it's a terminated, I think it actually terminates at that point. So 0.031. Okay. And then the other half I need is P prime of 5. So I need to take the derivative of the P function. And I will get 0.08t. And now we just plug in, what do we plug in? 5. We plug 5 into that. And well, this one you can do by mentally, 0.4. Well, maybe you can do mentally if you're alert. All right. And so we have this. We have a product of these two decimal values for our answer. And so now we just probably we use a calculator for that. You can check that you'll get 0.0124. And lastly, we should put units. Since this whole problem is a word problem, there are units for this. So it's ppm per, well, ppm of what? ppm, parts per million, of carbon monoxide per year, right? So the question was asking, at what rate will this carbon monoxide level be changing? Well, our answer, it'll be changing at a rate of 0.0124 parts per million per year. I did try to actually check if this number makes sense real world. I think it doesn't, but I'm not totally sure. But the process, I think, is right. So I'll admit that like it took me a little bit of time to figure out how to do this without it being so messy. I think this is the best way I can come up with for doing this calculation. So, all right. Well, any questions? If not, then I guess we'll stop the recording.